Hey everyone, welcome to this third discussion video. In this video, we're going to be going over the material for Module 3 on semiconductors, communication, and control. So here I've got the Canvas page open as always, and then I've got the intro slides here for you guys. So first off, semiconductors. Semiconductors are not fully conductive nor insulative. And so here is just a kind of spectrum of different materials and conductivity that they follow. So here we can see when the conductivity is high, we call these conductors, and things like iron, gold, copper, silver are good conductors. And here in the middle of the spectrum, we have semiconductors, so things like germanium and silicon are big ones that you'll see. And then on the right hand of this spectrum, we have low conductivity, which are things like paper, glass, ceramic, and so on and so forth. So semiconductor material can be either P-type or N-type, and this has to do with how we actually dope the material. Silicon, for example, can just be intrinsically no type, but when we want to make semiconductor devices that have some interesting uses, we typically dope them in order to have more P-type or more N-type. So for N-type, you can think negative. We're kind of injecting atoms with more valence electrons, so the silicon structure becomes more negative. And as for P-type, we kind of inject material that has a sh an kind of like an open space in that valence band, so you can think of more positive type there. So we've looked at diodes before, and diodes are actually two-terminal semiconductor devices, and we've explored the properties of diodes and how they can be forward or reverse biased. Right, so when we have the voltage at the anode greater than that of the cathode, we say it's forward biased. And when the diode is forward biased, it conducts as much current as possible. And you can see here with the ideal diode voltage or current voltage characteristic in the middle picture here. When this voltage, is positive, we say it's in forward bias, and you can see that the current just goes off to infinity, which just means that it'll conduct, as much current as physically possible there. Realistically, though, a diode characteristic curve might look like this on the right here, where it has some exponential increase, and it has some actual threshold voltage, right? This forward voltage drop, at which point we consider it to be forward biased. Um, and then there's also this reverse bias case where it does physically break down and allow electrons to go through if there's sufficient negative voltage applied. So we'll also be taking a look at transistors. So these are three-terminal semiconductor devices. And here I've just got an example of a bipolar junction transistor, which is actually available in our Elegoo kit. So there are two different, we call them BJTs. So there's this PN2222 and there's an S8050. And so these differ mostly in their electrical characteristics, and you can read about either one in their data sheet. But this is kind of how they generally look. So bipolar junction transistors have an emitter, a base, and a collector, and we'll get into what all that means shortly here. So these bipolar junction transistors are either NPN or PNP, and that just depends on how the structure, within the silicon is doped. For example, here on the bottom left, I have a picture of an NPN transistor. And as you can see, the silicon structure has two N-type regions and a single P-type region. And we'll get into kind of like how these behave and look at kind of like the regions of operation that a bipolar junction transistor can be in on Wikipedia soon. So BJTs are typically used to amplify current. Here, for example, the Arduino Mega board can only output 40 milliamps of current, and a lot of motors require more than 40 milliamps to operate. Some devices like the LEDs don't require more than 40 milliamps, but there are, of course, loads that require more current. So, for example, here I've got the DC motor in our kit, and so this requires 90 milliamps to run with no load here. So obviously we can't control it directly with just a digital pin, right? Because going back here, these digital pins can only output 40 milliamps of current. On the other hand, the 5-volt power pin can be used to control them to power the motor, right? Because it can output up to 200 milliamps, which is more than what we need, right? So the maximum amount of current that we would need to run the motor is 120 milliamps, and this is presumably at startup, right? When we're first turning that motor on, it might require a little bit more current. So we can also use the transistor as a switch. And so this is a little bit different than as an amplifier, but here I've kind of got it in a switch configuration. And the main idea is when I apply a positive voltage to the base terminal, right? So this is the base terminal. This is the collector. The collector is tied to the motor, and then the emitter is then connected to ground. So when I apply a positive voltage at the base terminal with respect to the emitter, then this kind of there are PN junctions within the structure of the transistor that actuate such that current will be allowed to flow from the collector to the emitter. And the easiest way to think about this is I basically have a diode here or some kind of switch. And when I apply voltage to the base, I can turn on the switch, right? I can close the switch and cause it there to be a short from the collector to the emitter. Or if I just have this base voltage at ground, then it'll be like opening the switch and no current will flow from the collector to the emitter. And so we'll take a closer look at that in the lab and kind of through some simulations. So this is kind of just a reiteration of what I just said here. When the PWM signal, right? So we're controlling with a PWM signal the voltage at the base of this transistor. And so when I turn the PWM signal high, I'm allowing current to flow from the collector to the emitter. And by doing so, I am providing power to the motor. When I have my PWM signal low, right, so this is effectively ground here coming out of the digital pin, and the emitter is also connected to ground. Well, you can think of that as kind of like opening up the circuit, right? So there's no longer any current flowing through the transistor. Practically there is a little bit, but for this simple first order analysis, there's basically no current going through. And so the motor is effectively switched off, right? So the motor kind of like loses some power, right? There's no longer any current. Well, some current is actually being sent back into the power pin through this, we call it a flyback diode. And that we include this flyback diode just so that the current doesn't try to escape into the digital pin where it might break the digital pin. Um, And so again, the motor is inductive, which means that the current can't instantly stop flowing, right? So when we shut off this switch and try to stop the current from flowing, the current will need to go somewhere because this motor, again, is inductive. And when something, right? So just like this little merry-go-round, right? So what we've done by allowing current to flow is we're basically pushing this little merry-go-round wheel. So it's going. And just because, we try to stop it doesn't mean that it'll just immediately stop, right? It'll take a lot of force in order to stop that merry-go-round from spinning, much like it'll take a lot of force to stop this inductive load, right? This motor from spinning. Um, and so what we'll do is we'll put this diode such that the current can keep flowing, but the current will flow back into the power pin instead of back into one of these digital pins or ground. Um, so now we'll jump into a discussion on communication. So communication is the transmission of information. Here I've got a bird. The bird's chirping, sending some kind of signal to surrounding birds, probably. And communication requires language for coherent transmission. Languages can have a set of symbols, such as the alphabet, and computers can speak various languages with binary. So it's a two symbol set, right? So we've got 0 and 1. We can convey a lot of different information with just these two symbols. Um, so electrical communication can be wired or wireless. So we have in the past uploaded code onto our Arduino board, and this is done over a USB connection. And what happens in the background is we write on our desktop the code, we compile the code, and then we upload the code onto the board. And so that can only happen when there's this USB connection. And so data is being sent through this USB cable, and it's going on to the microcontroller on the Arduino board. Um, some examples of wireless communication would be remotes. For example, we have this infrared remote in our kits, which transmits data in the form of infrared light. So this light is flashing on and off. You might think of this like Morse code or, just any kind of digital communication, really, right? So it's high and low. Um, so again, most electrical communication is digital, right? So we have this finite set of symbols, in our case, just 0 and 1 for binary. And this is mostly because computers are really good at processing digital data. So all these microcontrollers are designed to process digital data very well, and so it just so happens that a lot of our communication is digital. Um, so when we talk about communication, we're always talking about a transmitter and receiver. The transmitter sends data, the receiver receives data. Pretty straightforward there. But communication always requires a protocol. So these protocols are a set of rules for sending, receiving, and decoding data, and it usually has a way to wake up the receiver, such as a start bit, for example. In this picture here, we see the transmitter pulls down on the line, right? So the line goes low, and that indicates to the receiver that there's data incoming. So it wakes up and starts processing the data. So as mentioned before, there's this PC to Arduino board link, and this uses the UART protocol. This is the Universal Asynchronous Receiver Transmitter Protocol. It's a bit of a mouthful, but you'll see it a lot, and we'll kind of dig into what all that means here. But one thing to note is that you can actually look at this UART traffic using, there's some transmitter TX and receiver pins RX on your board. So we can actually hook up an oscilloscope and look at the data that's going on the line, which is kind of fun. So this is what actually going back real quick. So whenever we talk about communication, we like to talk about traffic, right? And that's just um, kind of like what is happening on those lines, those communication lines. So you'll see me refer to this as traffic, and that's kind of how we refer to it in general. Um, so here's what a UART frame looks like. It has a start bit, it has data bits, it has a parity bit, and a stop bit. So this is just an example of the frame. you can see that it idles high, which means that when there's no information being sent on the line will just be high. And so this has historical um, purposes, really. The main one is that in order to determine, if the line is dead or not, we like to see some kind of positive voltage on the line just to make sure that it's up and running. So a lot of communication protocols will idle high. Um, and so you can see when the transmitter pulls down on this data line, it indicates to the receiver that it's going to start data or start sending data. And these next few bits are data bits, right? So it's kind of like what the transmitter is really just trying to send these data bits over. There's a parity bit, and we'll get into what that means in a little bit, but in a nutshell, it's just used for error checking. And then again, the stop is just when the line goes back high and stays high, and kind of nothing else happens there. So infrared communication is very similar to UART. Instead of these pulses directly on the line, we have flashes of light. And obviously we need some kind of receiver module in order to look at the flashes of light and turn it into an electrical signal that does, go high and low. And so here's just an example of the remote control, which is something in our kit that does transmit infrared light. So we have this. So infrared receivers can detect light from a remote. And I just want to make the note that light can behave like a wave, and so it has a wavelength. And so we can actually detect certain wavelengths of light with this receiver module. And specifically, it's most sensitive at 940 nanometers. So you can see in this spectral sensitivity characteristics, it peaks out. It's 100% relative sensitivity at 940 nanometers of wavelength. So the transmitter flashes at a very specific frequency. So this is specific to the communication protocol, actually. There's a carrier frequency, which we'll kind of like explore during the activity. But in a nutshell, the receiver is looking for, first off, the correct wavelength of light, and it's also looking at very specific frequency of light, of the light flashing. So in a sense, it's filtering out two different characteristics of the light. So a lot of infrared communication uses this NEC protocol. So there's two different ways of encoding the data, right? Because we have a two symbol set, 0 and 1. Zero is a 562.5 microsecond pulse. So here, for example, is a 0, and you can see it's high for 562.5 microseconds, and then a 562.5 microsecond space. So you can see here that it goes low for another 562.5 microseconds. On the contrary, a 1 is 562.5 microsecond pulse. So here we've got that pulse. And then there's a much longer space with 1.6875 milliseconds. So the ones do take a little bit longer to transmit, but they use this method called pulse distance encoding, right? So the distance between pulses is, in a nutshell, what is being used to encode 0 and 1, right? So they're a little bit different. So that's cool. So if we connect our, so we've got this receiver module, and if we connect it up to the Arduino power, right? So we apply 5 volts and ground to the respective pins, and then we just look at um, the data, right? There's a ground, a power, and a data pin. If we just look at the data, we can actually see the incoming traffic, right? So the output of this receiver module should be a digital signal, right? High and low. Um, And I will say that writing code to process this NEC protocol data is hard. Um, we're not going to do that. We're going to use someone else's code. Fortunately, someone has written code that processes this protocol. This is this IR remote library. And so a few different libraries floating around. This one is by Armin Joe. I'm not going to even try to say that, but Armin. So I would try to find that one and get it installed on your machine. We'll be exploring it in this activity. So now I want to talk about control systems. So a control system commands or regulates other devices. This is the famous James Watt flyball governor, which was used to regulate steam, um, I believe. It's a very historical example that appears in a lot of textbooks, and you're welcome to read about James Watt and his flyball governor. Um, so a control loop can be either open or closed. And one easy way to think about this is if I have an open loop control, that means I'm not measuring anything at the output and I'm not acting based on that measurement. So I'm just kind of blindly doing something. When we have a closed loop control system, we're actually taking the system output, measuring it, and that measurement is in part changing the control action. So here we say the control action is dependent of the process, right? So we measure the output of the process and it has some impact on this actuating action. So LED lighting sequencers typically use open loop control, right? We just tell the LEDs how to turn on and off, like we did in the first lab, and then nothing else happens. Temperature regulation, on the other hand, will typically use closed loop control, right? We measure the temperature, and based on the temperature, we might actuate a fan if it's too hot, or we might actuate a heater if it's too cold. And we'll actually build up a kind of a crude temperature regulation system on, using parts in our kit, but the principle is can be easily applied to any kind of closed loop control system that you'll encounter in the future. All right, and so this is just going back to the whole idea that closed loop control requires a sensor, right? We need to measure the system output and feed that information back into the controller to try to um, cause the system to have some desired output. Um, so here's an example of a part in our kit that we can actually use to measure temperature. So this is a thermistor. They're extra sensitive to heat, and they do have um, thermal characteristics in a data sheet. So this specific one is said to have a negative temperature coefficient, and that's just because you can see as the temperature goes up, the resistance goes down. Right, so that's kind of like a negative slope. So the thermistor in our kit has a negative temperature coefficient. It's just something to keep in mind. There are positive temperature coefficient ones. Um, And then this is going into voltage dividers. So voltage dividers we have seen in the past. So they output a voltage proportional to resistance, right? So in essence, what we have is a top resistance and a bottom resistance. And this output voltage is proportional to this bottom resistance. Um, but things get a little bit tricky if we have variable resistance. So if I have this top resistance as an NTC thermistor and this bottom resistance as a fixed resistor. As the temperature goes up, this resistance, since it's negative temperature coefficient, will go down. Right? As the temperature goes up, the top resistance goes down. And so what happens is the bottom resistance starts to look larger, right, with respect to the total resistance of this network, right? So I've got this guy going down, so this effective resistance goes up, And so what happens is the output voltage starts to go up as the temperature goes up, right? Because as the temperature goes up, this goes down, this effective resistance goes up, so the output voltage goes up as temperature goes up. Um, so this is a really easy way to create a circuit that has an output that is proportional to temperature, and we can actually calculate what the temperature is if we know the specific characteristics. And so they've actually gone and done that in the Elegoo kit. So within the user manual, they have an example of how to calculate the temperature based on this specific setup, right? So we have the NTC thermistor tied to 5 volts, and then the other end tied to an analog pin A0. And then it goes also goes through a 10 kilo ohm resistor back to ground. And so what we've got here and from the user manual is this exact voltage divider, right? Instead of this V out, it's tied to the analog pin. And so we've created a voltage divider that has an output voltage proportional to temperature, which is great. So now we can actually measure temperature and use that. And I guess that's all I wanted to talk about. We've already looked at motors in the past, so kind of like what we're going to be doing this week is actuating a motor based on the temperature condition. So, that we don't really need to talk about the motor anymore. But thanks for tuning in. I'll see you guys next time.